Hello and welcome back to Engineering Simple. So I'll continue talking about line to ground faults on low voltage side of a system or a transformer and keep going basically. So these are the objectives of this video series. So I'd recommend watching the part one. So showed a three-phase. So I was drawing the three-phase system, but it got kind of clustered and kind of hard to deal with. Then I showed that when we are dealing with power systems, especially in steady state, we just draw the one-line diagram, which is simpler and it carries the same information. So I stopped here. So it's important to set up the the problem and make sure you understand like what is the system, then then it's a lot easier to draw the sequence networks and go from there, in the calculation of all the currents. So now I'm going to draw the sequence network. So for the positive sequence, so that's positive. So I have like the equivalent source here. Then I have system A, which is 345. Then I have some impedance of the system A. So this is positive sequence. So 1 means positive of system A. In this case, it's 345. And we have terminal H. So basically, I'm taking this one-line diagram and kind of extracting the sequence components from it. Because to calculate the line to ground fault currents, you have to use these symmetrical components. So H, then so basically we have the transformer. It has some impedance and it's positive. Then you have the T model T model. So you have the positive sequence, and I'll explain what these mean. Then you have positive. So 1 means positive, basically positive sequence. So X. So you have the X terminal or X bus or side, whatever you want to call it. Then you have the positive sequence impedance of system B. So you have system B, and again you have the equivalence source. So basically, I'll get a highlighter just so what I drew here. So basically, looks like the highlighter. I'll just get a different color. Oh, sorry, it skipped a pin. Okay, so this, let me just erase so it's not confusing. So basically, so from H to X, so this got erased. So we have X here. So basically, what I highlighted here, and I need to highlight this side here too. So that's the T model, the equivalent T model of the positive sequence of the transformer. In this, basically you would obtain from testing. And so we have a ground here, and this side here is grounded, so they're basically electrically connected. But this, in the positive sequence impedance, this is open. That's why typically in the positive sequence, you would not see the T model of the transformer. You would just see the positive sequence impedance of the transformer. But keep in mind, if you have three-winded transformer, basically you can get the T model. And the way you would calculate the impedances of the positive sequence impedances of the T model, basically you would apply kind of like the short circuit impedance of the transformer. You would apply voltage to one side, like the high voltage, short the low voltage side, and leave the Y side open. So that would give you the impedance from the high to low. Then you do the same thing. You apply voltage to the low voltage, short the high voltage terminals, open the Y. It will give you the same impedance. Then you do from the high to the Y, and then you can there's a formula how to convert from the impedances from high to low, impedance between the high voltage and low voltage, high voltage and the tertiary or the delta winding into the winding. Basically, what you would get from testing is ZHX. That is the impedance from the high side to the low side. Then you would get the impedance ZHY from the high side to the Y, and so on and so forth. Then what you would do to calculate H, for instance, is there's an equation 1/2 of, so you would take ZHX plus ZHY minus XY basically. So you see you sum up the ones that have the H terminal, and then you subtract the one that doesn't have the H terminal. That can be another video, but I just want to mention how kind of you get the T model for the positive sequence. In previous videos, I talked how to calculate the T model for the zero sequence impedance, but keep in mind that you can do the same thing for the positive sequence impedance. Okay, so that's the positive sequence impedance. Now let's do the negative sequence impedance. So the negative sequence impedance basically is just like the positive sequence, except there is no source. So the negative, I'll just do 2 system A. So H, Z2H, so Z2Y. So this is, sorry, this is 2. So you do the same thing as Z2X. So you have the X terminal. And Z2 system B. So you have B system. So basically, they're they're the same. It's just, and these are connected basically to ground. Both systems are grounded. So the only difference is the positive sequence, you have the sources. The negative sequence, you do not have this source. So that's the negative sequence impedance. Now, let's draw the zero sequence impedance. The zero sequence is a little bit tricky. And again, positive and negative sequence impedance. When you do the T model, you show so this is basically just a transformer. The equivalent T model for the negative sequence impedance, and you see it's open. So basically, the tertiary or the tertiary branch, it's like it does not exist. That's why typically you would just see ZHX, which is true, because if you sum this impedance here plus this impedance, they should give you the true impedance, or basically the impedance between the high and the low. So I just want to make sure you don't get confused if you are not familiar with this representation. So again, the zero sequence impedance. So here's A. We know there's a ground here. So zero sequence impedance of system A. So I'm going to do H. So you have Z0 H. Then in this case, Z0Y, basically it's connected to ground. So because the tertiary will be in the circuit. Then you have Z0X. So you have X terminal here. Then you have Z0 system B. So system means the equivalent impedance of the system. Instead of drawing all the things that are connected, we just kind of write the equivalent impedance because that's really what matters. So we have system B here. Then this is grounded. So this ground here is connected to this ground. So now you see the tertiary is in the circuit. It's no longer open. So now I'm going to use a different color. So what I'm going to do, I'm going to apply a line to ground fault, so to the low voltage. So your X is low voltage basically. So I'm going to connect this to the ground. So the X is connected to ground, and the same thing here. So you see the is connected to ground. So that's the fault basically. And the same thing here. So what would flow here is 3I0. So that's the total zero sequence current. So it's 3 times, because really what would flow here says 3I0, and we know I0 will be the same as I1, the same as I2. So the zero sequence current is the same as the positive sequence current, the same as the negative sequence current. But obviously what would flow through phase A? So in this case, we'll assume phase A line to ground fault. So basically this here, phase A, it's 3I0. That's what will flow through the system. So now what we want to do, so basically so if you notice here, so since this is open, really does not come into the equation. So basically you can ignore it. So assume it does not exist. So what you have in the positive sequence, you have this impedance plus this impedance, since this here is connected to ground basically. So you have these 1, 2, 3 impedances in parallel with this impedance basically. And the same thing, this plus this is in parallel with the system B negative sequence impedance. You can assume this really does not exist because it's open. So for the zero sequence, it's a little bit different because you have this impedance here is in parallel with this impedance. Then whatever that equivalent impedance is in series with this impedance here. So you would do the sum. Then that equivalent impedance is in parallel with the system B impedance. So here, let's call this current that flows here is AI we'll just call it 1 positive H. So basically the high voltage current in the positive sequence network. And we can call this, since here kind of it's not the same current, then we'll just call this I1X, the positive sequence current that flows through the low voltage. And we'll do the same thing here. It's I2H, and this, no, sorry, this one, it will flow here basically. I2X. Then this current here we'll call, since this here flows in the high voltage, we'll call I0H. So keep these currents in mind. And the tertiary, or the Y, I'll just call that I0Y. Then this here, since it flows in the low voltage, we'll just call it I0X. So it's a little bit messy, but if you follow through, it will make sense. So now in the next video, I will kind of simplify this diagram here, then start calculating the equivalent positive sequence impedance, the equivalent negative sequence impedance, then the equivalent zero sequence impedance. Thank you for watching this video, and be on the lookout for the next video. So we'll continue.